Hey, I'm Gaur and welcome back to the Beginner's Guide to DCTL Development, where today we're building a Hue versus Hue tool start to finish. As you can see from the length of this video, it's quite the process, and well, first off, we'll have to set up our UI parameters. Then we'll have to somehow create a Hue channel, because, out of the box we're working with RGB channels instead. So we'll have to get a Hue channel, then we'll have to shift that Hue channel somehow, and then qualify using the same Hue channel to, only change a specific hue range of the original image. And finally, we want to show that qualification in actually two different ways. So without further ado, let's start coding. So to start off, we'll first have to get the boilerplate, which I have now uploaded to my GitHub. You can find the link down below in the description. And we'll choose the KH boilerplate, not the texture one, because today we're not doing spatial operations, we're just doing a normal pixel by pixel DCTL. So simply hit copy raw file and head over to VS Code. Now I have created a new file, a new DCTL, Hue versus Hue, but you can, if you'd like, continue with the previous file. As a first step, let's just, without changing anything, save and check whether it runs in Resolve. I have found the DCTL, I'll hit reload, and yes, the line appears on top. And because I have changed the ODT that I'm using, I'm doing some custom stuff, this extremely neon green value actually shows up as white. So instead, I'll change it to 0.5, and that's much more clear. Now, I have confirmed that the DCTL runs, which is a good start. Next up, we should define the UI parameters. For this one, we'll want 3 sliders and 2 checkboxes. So I'll delete the value box and the int slider, not going to need those, nor will we need a drop down. And I'll copy the float slider twice by holding down Alt and Shift or Option Shift and pressing the down arrow. And I'll copy the checkbox once. The first slider is going to be our target hue. This is the specific point on the hue gradient which we will be targeting. The hue range is from 0 to 1, but I think it would make sense for the user to also be able to go in the negative direction, because it's quicker to go in the opposite direction than to go from one edge of the slider to the other to get an adjacent hue, because hues on the gradient start looping. Both ends of the hue range are red. And let's give it a parameter name of target hue. Now the next slider will be our target width, as maybe the user only wants to target a very small part of the adjacent hues, or maybe if you want a very large part of the image to be selected. Now this one will be from 0 to 1, but the default should not be 0 because, well, you do want to select at least some part of the hues. So we'll set it to 0.1 as a starting point. And let's name it target width. The last slider will be our hue shift. Now this is how much we'll be shifting the hue of the qualified parts of the image. Qualified by the target hue and target width. And for this one, we want to be able to go in either direction. So we'll set the minimum as -1. And also the parameter name of hue shift. Now for the checkboxes, we also want to give the user some kind of a way to visualize which parts of the image they have qualified. For that, let's have highlight selection, which will only show the parts of the image that have been qualified, and for the rest, it'll be a checkerboard. Let's simply name it highlight. And to give more variety, let's also have a matte mode, which simply shows the underlying matte as a grayscale image. And name it highlight matte. Now that we have our UI parameters in place, let's move to the first functional part. In this case, we could either start with the qualification process, but I think in this case it makes more sense to first implement the hue shifting. Now when it comes to what we're working with, it's red, green and blue color channels. There's no hue channel, so we'll have to transform from our RGB color model to some other color model that does include a hue channel. In this case, I'll go with HSL, meaning hue, saturation, luminance. And if you'd like a challenge, at this point you could just start Googling and try to implement this yourself. But for the rest of you, head over to my GitHub, choose code snippets, HSL, and copy these two functions, RGB to HSL and HSL to RGB. And let's paste them above our UI parameters. You could also paste them below the UI parameters, but this is just how I like to work. I have tried to comment what's happening in here as much as possible, but you don't have to understand how these work. Just know that if you give RGB to HSL an RGB value, it will spit out a HSL value. And if you take that HSL value and give it back to the HSL to RGB function, it'll give you back the original RGB value, as long as you haven't changed the HSL in between. But if you have, it'll give out a different RGB value according to what you have changed. Now to implement the hue shifting, we'll first have to go from RGB to HSL. So simply take the output and set it equal to RGB to HSL and feed that function the current image. Then in between we can do our shifting, and after that we'll want to go back to HSL. Hit save, and let's head over to Resolve and make sure that it still works. If I hit reload, in theory we should still see the green line, which we do. And if I enable and disable the DCTL, nothing about the image should change other than the green line, and that indeed seems to be the case. Now if we would like to see what the HSL functions are doing, we can for example disable the second one, head back to Resolve, hit reload, and you'll see something quite horrific. Why does it look so bad? Well, your monitor isn't designed to display the HSL signal. It's designed to expect RGB, which in this case it's not getting, and as such it looks pretty bad. So let's uncomment this line once again, and much better. Now to shift the hue, we want to add to or subtract from the hue channel, which in this case is the first channel, as is suggested by the name HSL, hue, saturation, luminance. To access the first channel, we want to type out.x. This is because float threes always have their channels mapped as X, Y, and Z, where with RGB signals, X would be red. In this case, X is hue, as it's the first channel. And to add to that channel, we can either type the longer version of equals out.x plus and the amount we want to shift by, which is the parameter. Let's hit save and see if it works. Reload. Still nothing should happen except the wonderful green line at the top. But if we play with the hue shift slider, the image will go quite crazy, and as we can see from the vector scope, the whole image is being rotated, which is exactly what we would expect. And just to show you a shorthand of this line, if you're adding, subtracting, multiplying, or dividing the original value, you can leave out the first part and just do not equals plus, but plus equals. Hit save, and it should function identically. Now, we have implemented the hue shifting part itself, but now we want to limit it to only a selected part of the image. We want to qualify by hue. To do this, we need to look at the initial image, but not as RGB, but as HSL. So what I tend to do is create another in variable, float free, but instead of in RGB, in HSL, and I create it the same way as down below, RGB to HSL, but instead of out, as we haven't defined that yet, I will use the in RGB variable itself. Now that we have the initial image as HSL, we can start qualifying it. As a very rough example, we can do the following. After applying the hue shifting, and I'll bunch these together to signify that they're one function, and add a comment, this is the hue shifting. And after doing the hue shift, we want to blend the original image with the shifted version, based on a qualification. Let's define our hue matte, and let's define it extremely simply. Is the given pixel within our hue range? Take the inHSL.x, so the hue channel. Is the hue of the current pixel bigger than the minimum, which is our target hue minus our target width divided by 2, because we want to set our total width, not the radius. And is the hue of the current pixel smaller than the target hue plus the target width divided by 2. So what we're doing is setting a range around the given target hue. Now this is a conditional, and if both of these are true, hue matte will be set to 1. As in this case, we could also call it a boolean, but as we'll be doing something more advanced in a minute, I'll call it a float already. So if both of these are true, it will return a 1, and if either one of these or both are false, it will return a 0. And finally, we want to mix the original image with the shifted version. To do this, let's set out to the original image times 1 minus the hue matte. So we're looking at how bright the hue matte is between 0 and 1, and we're taking the inverse amount of the original image, because the brighter the hue matte is, the more we want to take off what comes next, the new image, which is actually the current out, that we're just overwriting with this line, and we'll times that by hue matte. So we're adding together some amount of the original image and some amount of the shifted image, and those amounts are the hue matte and the inverse of hue matte. Now in theory, if we hit save and head over to Resolve, this should work. Okay, we still have our green line. Let's try shifting to hue. Okay, the hue shifting is still working, and it is confined to a certain part of the image. If we shift the target hue, you can see different parts of the image are being manipulated. And if we change the target width, then yes, indeed, we can make the qualified area much more fine. But what's the problem with this? Well, the selected area has a very, very steep fall-off. In fact, it doesn't have any fall-off. And if we were to represent this in the built-in qualifier, then it would look like this. No softness, just hard lines. Now, we have two options here. One is to mimic the way that Resolve does qualification with these triangle fall-offs. But what I personally prefer is using something even smoother, which is a bell curve. This is how it looks. You can define a center point and the width. As you can see, only a single point is qualified completely, as it is set to 1, and all the adjacent values gradually start falling off. And to implement this, you can go to my GitHub and copy-paste this bell curve function. Now do note that I'm using a custom power function, which I have also defined, and this is because the way the powf function is implemented in Resolve means that it can work differently on different platforms. And we don't want that. We want our tools to work exactly the same on every platform. And because of that, I have made a custom PowerF function, which I also recommend you use in every one of your tools. Now this bell curve function takes in the input, aka the x-coordinate, or the point on the curve we're looking for, the center point of the curve, and the width of the curve. So what we can do is replace all of this with the bell curve function. As the input, we'll have our input HSL image Hue Channel. As the center, we'll have P target hue, and as the width, we will have the target width. Let's see if this works. Hit reload, the DCTL still runs, and if we change the hue, well, it looks much better. And even if we decrease the width, it's much less prone to breaking in radical ways. Yes, if you zoom in, it doesn't look the cleanest, but at this point it's less about our implementation and more about the fact that there's just noise in the image. That's just the inherent limitation of HSL qualifiers, and also why many colorists try to avoid using the HSL qualifier. But as long as we stay above a certain width, we can even set this as the minimum. For example, 0.05 looks quite good, so I'll just head over here and set that as the minimum value for this slider. So it would be less likely that the user can break their image. Now let's see if there are any issues with this qualification. And to make it more clear which areas of the image have been qualified, instead of fading between the original image and the shifted image, let's fade between the original and just a red image. I'll set the red channel to 50% and keep the green and blue at 0. Head over to Resolve, reload. Seems like I have made a mistake. There we go. Instead of make float, it's make float 3. Reload. And there we go. We can very clearly see which areas have been qualified. Now, if I start going into the negatives, aha, nothing gets qualified. Okay, and if we go into the positives, things get qualified, but the qualification does not loop. Because in theory, both 0 and 1 should be targeting red. They should be equal. But as we can see, they are clearly not. To fix that, I tend to do the following. I create a second function, a second version of the bell curve, and call it bell curve looping. It takes the exact same variables, but creates 3 different versions of the bell curve. There's the normal curve itself, but then there are 2 other versions, the start curve which moves the center 1 rotation backwards, and a third one, I'd call it end curve, which moves the bell curve 1 rotation forwards on the Hue wheel. As such, we have 3 different versions, and one of them is bound to qualify the range we expect it to. But we don't really know which one of them it is going to be, so let's just get the maximum value of all 3. So in returning, let's use the fmaxf function, which returns the maximum of 2 floats, and because we want to get the maximum of 3 floats, we just have to use 2 instances of this function. Inside of one, let's do curve and start curve, and inside the second one, we find the maximum of the first maximum function and the end curve. And this value is what we're going to return. Let's just copy over the function name and replace our current bell curve with this new looping bell curve. Head over to Resolve and see if it works. Now if we go to the end, once again, it comes back and qualifies our skin. And if we go in the negative direction, even -1, once again qualifies our skin tones, so it's working as expected. Perfect. But let's be honest, this way of showing to qualification isn't very elegant. So as the last step, let's implement a nicer way of highlighting to qualification. For this, I'll first undo what I did here, and I'll once again mix the original image with the shifted image. Let's make sure that this still works. And yes, indeed, it does seem to work. And because this is going to be quite a bit of code, let's create a separate function right off the bat. It will return a float-free, an RGB image, with the transparency overlaid. As such, let's call it draw transparency overlay. And it will take in the RGB input image, then the matte that we want to display, the matte mode, meaning whether it should show the checkerboard or just the black and white matte. Then for the checkerboard, we will need the X coordinate, we'll need the Y coordinate of the current pixel, and finally, in order to have the checkerboard appear the same size regardless of the resolution, we also need the height of the timeline. So these should be all of the different parameters we'll need. And first, let's implement the simpler version, that being the black and white matte. As always, the way I like to do my functions is to first define the out, and as a safety, I'll set it to in. Then return the final out. And in between, do whatever. In this case, if we want to draw the matte as a black and white image, all we're really doing is setting the output to a float free consisting of the matte 3 times. Let's just copy this function and implement it after the hue shifting, because we don't want to do any hue shifting on the transparency overlay. We want to show the transparency overlay after we have done everything else, but still have the green line show up on top of the qualification highlighting. So let's have an if statement, because we don't want to show it regardless of the checkboxes, but we only want to show it if the highlight checkbox is checked. And if it is, let's set output to this function, and let's see, just copy paste all of these variables and see what we have, what we don't have. So as input, we have our out. As the matte, we have our hue matte. As the matte mode, we have our P highlight matte. And now for X, Y, and height, as we can see, we do have our X, Y, and height, but they're integers. So we'll have to turn them into floats rather simply by casting them, which means to just force them into the float format. So we'll have float px, float py, and float p height. There we go. And in theory, if we save, head over to Resolve and hit reload, things should work. Nothing changed because we haven't checked highlight selection, but if we do, wonderfully, it does seem to work. The brighter the area, the more selected it is, and the darker, the less selected it is. Perfect. And finally, let's implement the checkerboard version. For that, let's first implement an if statement, because we only want to use the black and white version if matte mode is true. And if it is not, then we want to draw the checkerboard version. First we'll need the checkerboard's color, which we can set it to, for example, 0.3. This is the value we'll set the red, green, and blue channels to, so it'll be a grey color. Then secondly, we'll need the square size of the checkerboard. And as I said before, while you could hardcode a specific pixel size, I like to make my tools look the same regardless of the timeline resolution, and as such, I'll make the square size relative to the height of the timeline. So in this case, I'll do height divided by 32. Next up, we'll have to calculate whether to draw a brighter pixel or a darker pixel to create the checkerboard pattern. For this, let's calculate the current row and column of the pixel. And this can be done by dividing the x-coordinate by the square size and the y-coordinate by the square size. But because we want the index of the row and column, not the exact coordinates, we want to floor them, which means to round them down. So as a result of these calculations, we will get integers or whole numbers that tell us which row and column the current pixel is in, row and column of our checkerboard. And now to paint every second pixel a darker color, we can check if row plus column, when divided by 2, has a remainder of 0, meaning if it is an even number. And if that is the case, let's set the transparent color to a different color, for example 0.35. Finally, we have to set the output to the transparent color. And because as an output we need a float 3, let's just duplicate the transparent color 3 times. Let's hit save, and what we would expect is if we check highlight selection, we'll just get the checkerboard, which works beautifully. But it is not the end result we're looking for. What we want is to see the qualified image on top of the checkerboard, and for that we will once again do the same as we did down here, which is mix between two images, in this case the checkerboard and the original image. And by original image I don't mean the original input, but the original image that this function is getting. Now we could just copy paste this, but because we are doing the same thing multiple times, it makes sense to turn this into a separate function. So let's copy this line, head over above the draw transparency overlay because we have to define a function before we want to use it. It'll return a float 3 and let's call it mix float 3. It'll take the mix as a float 3 called, let's call it just in A, and float 3 in B, the two float 3s that this function will be mixing between. Then we can paste in the code from below and very simply just return, and instead of in RGB we have in A, instead of out we have in B, and we can replace Hue matte with the mix. So now we have the exact same thing that we're already doing, but as a reusable function. And right away we can even replace what we have here. So we have Hue matte as the mix, in RGB as in A, and out as in B. So this should do the exact same thing, but it's much more readable as to what it does. And now that we have this function, we can also use it here, where instead of just setting the out to the checkerboard, we can mix it between this checkerboard color and the original image, depending on the matte. Then our in A, which is the image we're fading or mixing from, is the checkerboard, because if something is not qualified, the matte is dark, which means we want to see the checkerboard. And our in B for the mix is going to be the original input image, which is the qualified part of the image. So let's save, head over to Resolve, hit reload, check highlight selection, and there we go. A beautiful way of highlighting the selection where you can clearly see what is highlighted and what is not highlighted from the darkest pixels to the brightest pixels. Unlike if we look at how Resolve does it, if we highlight a certain range of pixels, they're shown on a grey background. But what if those pixels happen to be grey as well? Well, you can't really see them, can you? So that's why I like to have a checkerboard instead. We can now select a hue we want to change. For example, let's qualify the plant, disable highlight selection, and let's give it an orange tint. Let's quickly check that our matte works. And to keep in mind, to see the matte mode, you do also have to check the highlight selection. And yes, the matte mode still works. Last but not least, we should comment out the green line by adding 2 slashes in front of it. Save, head over to Resolve, and I'd call this a finished tool. Now, what can you do from here to improve the tool even further? First off, go over your defaults. For example, should the default hue target be that of skin tones? Because users tend to target skin tones and want to, shift them a tiny bit to get them perfect. And if you think about how a user uses this tool, what's the first thing to do? Qualify. What do they need to do to start qualification? They need to check the highlight selection. So why not have it highlighted by default? Secondly, go over the ranges. Because does the user have to be able to rotate the hue 360 degrees? Probably not. Most likely they'll be rotating within 30, 45 degrees, if even that. And thirdly, icons. Icons can make it a lot easier to quickly grasp where which slider resides. Well, that's it from me. See you next time.